Okay, I think we are ready. So we were discussing the assignment. So what about you? You have done. So one was the epsilon NFA to NFA. Yeah. Those were also there in the notes, I believe, right? If you look at the notes, so they should be anyway there, but that should be there in some textbook also. What we did in the class was epsilon NFA to DFA translation, but you can also do an epsilon NFA to NFA. The other one was the perfect shuffle, which we already did. And then what else was there? So there was this odd of n, which also you could do. Okay, so odd of L also you could do. What else? Sorry, union is regular. Can you speak up a bit? One of them is finite. Then why it should be? Okay, so could you say what the question was maybe? Um, Sorry. Are you able to hear me still?
Yes, sir, I'm able to hear you.
Okay, okay, good. Just a moment. 50. Okay. So what was the other problem that we, so what was the problem? Can you?
Yes.
L1 union L2 is regular and L2 is finite. Then show that L1 is regular. Right? So this was the thing. You did it? How? Closure properties. How did you do this? So if L2 is finite, then L2 is also regular. Okay, then. So that means L2 is regular. So then you are saying L1 intersection L2 is finite and hence regular. Okay. Oh. So L1 union L2 intersection this. Okay, so what does this give you? So this is the same as L1 intersection L2 prime, correct? So this is the same as L1 intersection L2 prime. So then, I mean, but here you were saying, so you were saying that this is equal to this. Is that what you said? Why? Because, yeah, exactly. So L1, so let's see. In fact, you have, like, you can consider, like, here you have some L1, and maybe this is your L2, right? This is your L2. And now you are saying that intersection L2 prime. So intersection L2 prime. So you get all this region, right? L1 union L2 intersection L2 prime. Okay. So you get precisely L1 minus L2. right? L1 intersection L2. Then what? Sorry? Could you repeat? Yeah. So after this, so this you get like L1 minus L2 and then L1 intersection L2. Now L1 intersection L2 is regular. So what we got is like this is regular and then you can take the union with L2. This is also regular. So you get L1 is regular, right? So these are very standard like set theoretic operations. And so the other ones also you did right? The odd thing and so, but what about epsilon NFA? No, so could you make an epsilon NFA? So what was the odd language again? Like I think we had it sometime, right? Okay, let's go back to one of the previous lectures. It should be somewhere here. So here it is, the odd language, right? So we are talking about this. And how did you do this? Keep two copies. Keep two copies and then, so essentially, Ankit, like, so what he's saying is that you keep two copies of the, so you have one copy of the DFA, you have the other copy of the DFA of this L, right? Is it okay? So you have two copies of the, suppose this automaton is A, here the automaton is A, you make another copy, and then what are you doing? So let's say this corresponds to the even copy, and this corresponds to the odd copy, right? Correct. So if you are starting from here, then for every transition, you will go to this. You start from even, okay? So if you start from, let's say even, okay? And maybe then from the even, you will come to the odd copy, right? And here, this is, let's say A1. And this one will be the other. So here on this side, you will have maybe A2 like this. Huh? No, okay. So initially you will start drawing it like this, right? A1 and A2, and then you will replace the A2 with an epsilon, correct? And can you formally write how it will be? Like if you have to define formally the epsilon automaton. Yeah, the transition function and the state space. So the state space is going to be like, as we discussed, it's going to be Q1 cross 1, comma 2. So 1 is for the even, 2 is for the odd, right? And then you can do this, correct? So is it clear, Ankit?
Yeah. Now I can try.
So, huh?
Now I can try.
Yeah. And the other one you saw, right? It's just a standard state
Yeah.
operation. The other question that we discussed,
Yeah.
right? So this is what we discussed, that if it is L1 union L2 is regular and L2 is finite, then show that L1 is regular. Correct. So what did we do? You can just draw a Venn diagram like this, and then you can try to figure out what kind of operations. If L2 is finite, of course it is regular.
Yeah.
Right. So it is essentially you have to take L1 minus L2.
And L1
right?
intersection L2.
Yeah. Right. And L1 minus L2. So the only tricky part is like L1 minus L2, you can write it in this way. Okay. L1 union L2, which is given that this is regular intersection L2 prime. Right. And then this is, and you can then take the union with this intersection part. Correct. And then
Yes.
it's all closure properties that we saw, standard closure properties, and it becomes regular. Clear?
Yes, sir.
Okay. Good. So what did we discuss last time? So we were talking about regular expressions, and we talked about the star height problem, right? So the star height problem, what was it? The number of nested stars. And what is the, so that is the star height of the regular expression. And what is the star height of a language? The minimum possible over all such regular expressions. And what is the star height problem? Given a language, find the minimum possible star height of the language, essentially. So that is the star height problem, right? And what we said, what we just mentioned, is this was a difficult problem which was open for a few decades, and finally it was solved, but it's a fairly non-trivial algorithm to solve it. In fact, there exists some algorithm. And also what we studied is also there can be a family of languages, right? For every natural number, you can construct a family of languages such that the star height of that language equals that natural number. For every natural number I, there exists a language such that the star height of that language is equals that natural number. Clear? Right. So what we discussed is that now today we are going to talk about extended star height problem and also this finite power property. Okay, so these are, we'll start with this. So let's recall, so now you have to tell me. So what is the syntax of the regular expression? So what is the syntax of regular expression? What all things do you have? You have like a plus. What else?
Concatenation.
Concatenation. Then
And then
star.
this star.
What else?
Empty set.
Exactly. So we also had the base cases, right? Epsilon, A, empty set, correct? And now, so this is what we say is this part is regular expression, right? Now, this captures, we discussed already in the last lecture, that this captures like the set of recognizable or regular languages. Sometimes regular, we also said, it's also called rational, right? Rational expressions. And this is recognizable sets or regular languages. Correct? And what else do you have? In the extended regular expression, so we are going to talk about extended regular expressions. What else do you have? You have R1 intersection R2 and negation of R1. Okay. So we are also allowing R1 intersection R2 or negation of R1. Sometimes I'm also going to write this as R1 bar like this. Clear? So now the question is that if I allow this extra syntax, this additional syntax in the regular expression, is it going to give you more expressiveness? Are you going to express something more than regular languages? What do you think? No, right? That's what you were saying. No, it's very obvious that it's indeed not going to be the case. It's not going to allow you more expressiveness because these are already equivalent to regular languages. And we know that regular languages are closed under intersection and negation and complement. Correct? So this is, of course, not going to give you more expressiveness. But the question is that by doing this, can you reduce the star height of the language? Is it possible? Right? So the question is, can it be the case? Is it possible? Is it possible that the star height of a language is strictly, it's more than the extended star height, right? So when I say extended star height, I guess you understand what I mean. So it's essentially in the regular expression, now you can use extended regular expressions instead of regular expressions, right? So this is the question. So what do you think? What do you think? Yes, no? You think no? So what do you think, Ankit?
So I'm not able to think anything, to be honest.
So is the notion of star height clear?
Yeah, notion of star height is clear.
Yeah, and is the notion of extended star height also
Yeah,
clear?
yeah, it's
Yeah.
clear.
Yeah. So suppose so what is the immediate language that comes to your mind with which has some star height 1? The first language that suppose comes to your mind. What is that?
A star.
A star. What did you say become? Suppose you have an alphabet sigma. What did you? Huh? I can't hear you. Okay, so you're saying that suppose sigma is just A, okay? And then you are saying A star. Now with extended regular expression, how can you express this? Sorry? Yeah, exactly. It's anything, any arbitrary, any word in this, with this for this alphabet, right? But the question is that how can you express this using the extended regular expression? I mean, of course, this is also in extended regular expression, but do you have anything? Phi complement, right? So phi bar, isn't it? Abhishek, sorry, Ankit?
Yes, yes.
Huh?
Yes.
In normal, yes. So if I am talking about sigma star for any arbitrary, any alphabet sigma, right? So sigma star is not the same as sigma, right? Or you can say, for example, sigma star, if your sigma is, let's say, AB. What is sigma star? It's A plus. The regular expression is A plus B star.
Yes.
Correct? The regular expression is A plus B star. Right? I mean, this is the regular expression. And now this is same as phi bar. Right? Correct? So now, of course, I have to define, for example, also what is the star height of these expressions. So star height of R1 intersection R2 equal to max of, just like we defined it for plus and concatenation, right? Max of star height of R1 comma star height of R2. Okay, right? And star height of negation of R1 equal to star height of R1. Clear? So of course, the star height here is 0 if you consider this extended regular expression, whereas for this regular expression, the star height is 1. Clear? So similarly, sigma star, sigma equal to AB, sigma star is A plus B star. Here you can consider this to be phi bar. Right? Yeah. So what is the regular expression for, let's do some simple exercises. What is the regular expression for sigma plus? So you don't have the, right?
A plus B dot A
Yeah,
plus
so
B whole star.
equal to A plus B dot A plus B star. Correct? Right? Now, if I have to, so this is the regular expression. Good, Ankit. So this is the
Yes.
standard regular expression. Now, what if I have to use? So this is the regular expression. Now, can you tell me if I have to use extended regular expression again, can I? So what is the star height of this expression? So suppose this is R, then star height of R here is 1.
Yes.
Now, if I consider an extended regular expression, what is the star height of that?
Star height of that. I can write A plus B in terms of intersection and complement, and so it should be A complement intersection B complement overall whole complement, and dot psi complement.
Sorry.
I'm saying A.
Okay, so here, okay, so there is one easy thing to see. So what does sigma plus doesn't have? So when I'm talking about this thing, so you see
Mhm.
that sigma plus is nothing but sigma star minus epsilon, correct?
Yes.
And one easy way to write this is epsilon complement, right?
Yes.
So what were you saying, Ankit? You had a different expression, but that may also work. I mean, I don't know. Let's see.
Yeah, it was
Is
A, A. I'm writing A plus B in terms of A intersection B actually.
okay. So
So
you are
that
saying A plus B, essentially. How are you writing it?
I'm writing in negation of A intersection negation of B whole negation.
Yeah, full negation. Okay.
And dot psi psi negation of psi.
Ah, okay. And then you are saying that it is a phi bar.
Yeah.
Okay. So okay. Yeah, I guess this should also work. So you cannot, you can have everything other than A. So A plus B. So it's either A or B. And let's check this. So you can have either A or B. And then you are saying, I can have, and here you are, this is essentially A plus B star. So this is very clear. And this is A bar intersection B bar and whole bar. So what this will have? So everything other than A, everything other than B, and then you take the intersection. So that will have everything which won't have A and B. So this is like sigma star minus A plus B. Exactly. And then you have, then of course you take the complement of that. So you have A plus B. Okay. A plus B and either A or B, and then you you are taking this thing. So this works. Yeah. So this also works. Good. Right? Yeah. But we also have the epsilon with us, and then epsilon bar is even simpler expression. Good. So right. Right. So this is what was suggested by Ankit. Okay, good. So you see that, so essentially the message that we are trying to give here is that uh, sometimes with extended regular expression, you can reduce the star height. Okay, so uh, suppose I want to say this. Suppose I want to say this, which is, so my sigma is, let's say, BB. Sorry, sigma is AB. And I want to consider all words, okay, without two consecutive Bs. Okay, without two consecutive Bs. I think this was something that we were discussing during the last lecture. Like if, okay, but anyway, so let's say we are talking about this without two consecutive Bs. So how can you do this with an extended regular expression? It's so one thing, as you see, like what we are using the power of the complement to reduce the star height. So in order to consider these two consecutive Bs, what we can do, you can think of words which have consecutive Bs and take the complement of that. Correct? So how do you write words which have this thing, two consecutive Bs?
A plus B whole star.
A plus B whole star, good.
BB
BB,
and then A plus B whole star.
right. So this is equivalent to phi bar, BB phi bar, correct? And now we said, so this is words which have two consecutive Bs. So for this one, for without two consecutive Bs, you can put another this thing. So phi bar, BB, phi bar, and then there's a whole bar. Clear? Okay.
Yes.
Right. So this is right. I mean, so this is an example of an extended regular expression. Right. Now, what are the questions again one would look at? So far, these languages we saw, they have extended star height how much? Extended star height how much? Did we see? Zero, right? Yeah. So far the languages we saw, like words without consecutive two Bs, right? And then we saw sigma star, we saw sigma plus, all of them have extended star height of 0. Correct? Now the question is that, so this is a homework problem. Can you think of a language? Can you think of a language that has extended star height just one. Extended star height equal to 1. Okay, so this is a question. Okay. And you may do some Google search here. Okay, I would recommend that try to do some search and try to figure out whether you can find it. Because just trying to think about it like on your own, it might be slightly challenging. So I would kind of rather recommend that for this homework, you can try to search and try to figure out like what kind of things are there in the internet you find. Okay, right. Um, so these extended languages with extended star height 0, these are also called star free expressions. These are also called star free expressions, right? So when I'm saying star free, it's considering extended star height. Clear? So these are called star free expressions, right? Or often these are called star free regular languages. Star free regular languages. Okay, which means extended star height is 0. Clear enough? So what we have seen that there exist languages with extended star height 0. We are asking this question that can you find out some language for which extended star height is 1? And it is known that indeed such languages exist. Okay, so you have to find out something. Okay, so you can try to do it yourself. If you can find something yourself, that's great. But otherwise, you can also try to go and search and let me know what you find. Okay, next, the big open question is does there exist any language with extended star height 2 or more? Right? Is it okay? And since this problem was posed, I think it was like in the late 1970s. So it's like almost 4 decades, right? So this problem is open. Right? It's so simple to define the problem. So you have regular expressions. I'm talking about extended regular expressions. I'm talking about, we saw languages which have star height 0, which are called star free, extended star height 0, which are called star free expressions. Then we mentioned that there exist languages which have star height 1. We didn't see that, and that's something you should try to figure out. You should try to explore and figure out and tell me some language. It's not very difficult. Those languages don't look very difficult. Just have to figure out like which kind of languages are not star free, So they have an extended star height of 1. And this question is open, that do there exist languages which have extended star height of 2 or more? Clear? Okay. So I'm just talking about like automata theoretic questions, the language theoretic questions that people often would like to study and which are open. And these are very easy to describe, but these are wide open. Okay. Now we will discuss something called a finite power property of a language. Finite power property. Okay. In short, this is called FPP. Okay. So what is a finite power property? So Ankit, you were still following any question?
No, no, I'm following, sir.
Okay, good. A set X, which is a subset of A star, is said to have FPP finite power property if X can be written, if X star can be written in this form: epsilon plus X1 plus X2 plus up to some Xk for K belonging to the set of natural. So for some finite K, right? So what is X star? X star is epsilon plus X1 up to its, of course, union of Xn. So this is X star, correct? In general, this is the definition of X star. But now we are saying that the set X has finite power property if X star can be represented as a finite union of its powers, starting from like star, right? I mean, so you have X0 plus X1 plus X2 and so on and so forth. Correct? So this is the regular expression. So this is a regular expression. I'm using the plus. So this is the finite power property. Now, this K is called the order of X. Okay, so K is called the order of X. Now, there's a remark that I would like to add, is which you can possibly see. If epsilon belongs to X, right? Then Xk is a subset of Xk plus, or maybe Xn is a subset of Xn plus 1. It's clear, it's obvious. If epsilon belongs to X,
It's not clear to me, sir.
It's not clear. Why?
Yeah.
So essentially, what is Xk plus 1? It's Xk dot X.
Okay.
Right? And what is Xk? So suppose Xk, and what is, how do you, so suppose this is suppose I call this A, okay? Suppose I call this A, so this is A dot X, right? And how did we define A dot X? This is equal to small x comma y, x dot y, such that X belongs to A and Y belongs to capital X, correct?
Yeah.
Okay. Or you can write this as small x belong to capital Xk and Y belongs to capital X, right? Now, if X has epsilon, then Y can be your epsilon, right? So every word that belongs to Xk will also belong to Xk plus 1. Is it clear?
Yeah.
Right? Okay. Or every word that belongs to Xn belongs to Xn plus 1. Correct? I mean, it's, sorry, I think I possibly confused you by this, by K and N, maybe.
No,
So
it's
let
fine.
me,
It's
so,
fine, sir.
yeah, Xn plus 1, here is Xn, and here this and this. So, yeah, right? Okay, is it clear now, Ankit?
Yeah.
Okay, good. Now, suppose if I ask you this question, consider finite language L. So now I say that suppose there is a finite language L. It's a finite language, or X. So X is a finite language, correct? X is a finite language. Now, finite language such that X has a non-empty word. So it means that it's not epsilon, right? So what I'm trying to say, it's equivalent to saying that X is not equal to this epsilon. Clear? This is what I'm saying. Okay. So the question is, does X have FTP? It's a finite language. You have finitely many words. So what is a finite language? It means finitely many words in X. It will not have FTP. Why? Yeah. So you consider any xk, so it will not have. So the answer is no. Why? Because you consider any xk, and then if you concatenate with x, right? You can always construct a word of higher length, right? Xk dot x has a word of length more than the length of all words in xk. Is it okay, Ankit?
Yeah.
Right? So for example, if you say your xk, suppose your x is just the set AA, right? So your x0 will have epsilon, x1 is AA, x2 is AAAA, right? x3 is 6 of them, correct? And so on, right? So you don't have any n such that x star is never equal to x0 plus x1 plus xk for all k, right? So it doesn't have the FPP, finite power property. Any question? Any question? Is it okay?
Yes, fine, sir.
Okay, good. Right. So let's, just to be a bit familiar, let's have this question, some examples. So what are the orders of these languages? A star plus A plus B star P. What is the order of this? What is the order of this? So that means, so is the question clear?
Yes, sir.
Huh?
Yes, sir.
Order?
I have to write x. I have to express x star in terms of x0, x1, and xk for some k element of n.
Yeah. So, so what is your question, Vikram? So what is, the question is, what is the order of X? So are you asking what is an order? Right? So order is what we saw, right? It's like, this is, the K is the order, correct? So yeah. What is the order of X? Hmm? 2. So Ankit, what is the order of this?
I'm not able to find order, sir.
So what kind of words? So how would you try to find the order?
No, I have to express this in terms of x0, x1, and all those things.
Correct. Yeah. So intuitively, what do you think? Like, first of all, so how would you try this? Like, so X star has some words which X doesn't have, right? But
Yeah.
those words will X2 have, and those words, and similarly X3 has, and so on, right? And so intuitively, if I ask you, like, which word do you think that X star has? So first of all, this is kind of not too difficult to see, right? So what word X star has, but X doesn't have, right? So give a word W such that W belongs to X star and W does not belong to X. Huh? ABA, right? What about, you are right. So you can have ABA, exactly. But even simpler is BA, right? Because there is a star here, right? So there is a word BA, correct? And so BA, where will it be, Ankit? In which, where will it be BA?
Where in sense of which
Oh,
order?
yeah, which like, yeah, exactly. Sorry, which power? So I mean that BA will be next to, or won't it be there? So this word BA.
Okay, so first I select B, then I select an A. So BA, it won't be there in x square, because if I select B, then I select A. Okay, then I have to have a in end. I have to have a B, sir.
No, but here is a plus, correct? And here is an A star.
Oh, oh, yeah,
So BA belongs to X2, correct?
yeah, fine, fine.
So BA belongs to X2. And in fact, now if you look at this thing, so ABA, right? So
Yes,
ABA also belongs to X2, right?
yes, because I can choose an A from the first, then B from the second, and again A from either from the first or no, from the first.
I don't understand what are you saying.
Actually, I'm just interpreting how it's like it's coming
Huh.
in X2, so that's it.
So how are you going to do the ABA? How are you going to
Yeah,
select ABA?
so like A from the first I will select, then
Okay.
B from the second part of the expression, A plus B whole star. Okay,
Huh.
and
Huh.
then again I'll go to the first one, A star. But the A star is the
Uh,
first part of this uh, left hand side of the plus sign.
no, but here is like, if you have chosen this already, you used your A, you say it from here,
Yeah,
right? And then you are saying that
B from A
uh,
plus B.
B from the second X, like, so you have X dot X. So you are saying where, which, so where your AB from the ABA, where does it come from? So this is like A star plus A plus B star,
B.
B dot A star plus A plus B star B. So where does the first A come from?
First A come from, sir, here A star, sir.
So you are saying the first A comes from this,
Yes,
then where
because if
does this
I
B?
yeah, second B
Then,
can come from either from A plus B star or from the B itself actually.
so the second B you are saying it comes from here.
No. It should come from A plus B whole star, sir. Because if I choose a B here, then I have to end it.
Yeah. So where are you? You are taking it from here.
I'm taking from A
Can
plus
you?
B whole.
Is that what you are saying? So you are
Yes,
taking this from here. Can you do that?
yeah, yes, sir.
Is
Why
it
can't
correct?
we? Yeah, it's A plus B whole star. So either A or B I can choose, or
No, but you have already chosen the A from this. Already you have chosen the here. So you have a plus here. You can choose either this or this, correct? And you have already chosen the A here, correct? So now you cannot use it anymore, this part.
Yeah, I cannot use it. So I have to choose this B, the second part of second B, because if I choose A plus B whole star, then I have to end it with a B.
Yeah.
So I can choose only from this B or single B I can choose, and then again I'll choose
okay, so I think so Big Khan, what do you think? How are you going to do this? Does it belong to this? Oh. Okay, so Big Khan is saying you can choose the AB from here, right? This you can do. The AB you can do from here because it is A plus B star B. So you can choose an A from this part and then the B from this part, and then the next A you can choose from this.
Okay.
Correct? Okay. And this gives you that.
But sir, I'm not able to see one thing, sir. That it is expression is A star plus A plus B whole star dot B. So once I have chosen AB from here, okay. Okay. I'm having a dot X actually. So that's fine.
Okay. So in fact, you can argue that this is enough. So in fact, you can argue that if you just think a bit more, you can see that in fact 2 is sufficient. So the order is 2. Okay. Now, quickly, can you tell me if I consider this language that X equal to A star plus A star B, what is the order? Is it FPP? Is this language FPP? No or yes? No. Why? So Bikhan says no. So why do you think? What do you think, Ankit?
Yeah, I'm not able to get it, sir. How do we know?
So because you can see that you can consider words which can have arbitrary number of B's, right? So you can have B. So for
B to I can construct X dot X dot X dot X dot.
Yeah. So BK belongs to XK, but BK plus 1 does not belong to XK for all K, right?
Yes.
Hence, it does not, X does not have FPP.
Okay, BK belongs to XK, but BK plus 1, okay.
BK plus 1 does not belong to XK. BK plus 1 belongs to XK plus 1, right? Hence, for you choose any K, right? So you choose any, suppose X4, right? B5 does not belong to X4, but B4 of course belongs to X4, right? And you can just construct all these sets and you can see that in fact it doesn't have FPP. Clear?
Sir, can you just go back once more? So I just want to see the definition of FPP once more. I got confused.
Yeah. So the definition again is, what is the definition? So you can start with x0 plus x1 plus x2. So you can define x star instead of as the union of all these sets, right? Okay. So this is a regular expression as long as there is some finite k for some k in N, for some k. Okay. So for example, here what I claimed in this, that x star here is x0 plus x1 plus x2. So the order is 2. Okay, so x star is x0 plus x1. This doesn't have FPP. Okay, I will give you another example and I will let you think about it. So suppose x equal to this language, epsilon union A2 A3 star.
Okay.
What is the order? I'm going today a bit slowly because I think, yeah, it may take a little bit of time for you to digest these definitions. Hence, I'm going, I mean, if you see, I'm going much slower than the last few lectures today. But yeah, so what is the order here? So this you can think offline, right, as another homework.
Okay.
Clear? So we talked about two homeworks. So one is extended star free, extended star height 1. So find such languages, right? Extended star height 1. So uh, this was a homework, right? Right. And then the other one, we are talking about this thing. So this language, what is the order? So the order. Okay. So you can think of this and tell me. Okay. Good. So now, so now the definition is clear. So the
Yes.
definition of the order, definition of finite power property, and so on and so forth.
So basically, I will say that let's say that X has got finite power property. Okay.
Yes.
Then I
it
will
has a
multiply.
finite order.
Yeah, it has a finite order, matlab, for some
Right.
finite k. So
K,
if
yeah.
so if it will not have a finite power, if I dot x, okay,
Yes.
and
It will not have a finite power
if I'm able to produce the next set of letter of words, okay, I have to keep multiplying x dot x and all those things.
Yeah, the next set of words, essentially it means that if you have x star, so this x star, you have to, like, you cannot stop it. Like, so essentially x0 plus x1 plus x2.
Yeah.
If you can do this for some finite k, for some k,
Yeah.
right? It can be anything, like it can be even 100, 200, 2000. As long as it is finite, then you say that it has finite power property.
Okay.
Right? And then another question, again, you can search. So does there exist an algorithm? Given, does there exist an algorithm to find the order, right? This is a natural question that should come to you. Does there exist an algorithm? Given a regular language X, regular set X, a rational set X, does there exist an algorithm to find the order of X for an input regular set X? Right? Again, try to find this out. Right? So this is another homework. I mean, I can state it, of course, but why don't you go back and do some search yourself? Okay, good. So today we'll start with another topic, which is called finite. So now I will go a bit faster because I think this you will be able to understand easily. So finite automata with output. Okay, so we are going to define two kinds of machines. One is called a Moore machine, the other one, but stop me if you have questions. Okay, just stop me if you have questions, or if you kind of get lost somewhere, just stop me. So I'll just try to move a bit fast, but please feel free to stop me whenever you have a question. Okay, good. So what is Moore machine? So Moore machine are automaton with output on states. I'll define what it means. And Mealy machines are automata with output on transitions. Okay. Now you can think of like there is a state in a DFA, right? You can think of this as DFA. So this I'm talking about the Moore machine. And whenever you are visiting the state, there is also an output associated with it. So you are visiting the state. So suppose you come from some state Q0 to Q1, reading an A, and there is an output associated with it. Suppose this is 1, this is 0, and so on. So I can have different input and output alphabets. So maybe my input alphabet is A, comma B, and my output alphabet here may be 0, comma 1. Correct? So I have, every time I'm visiting a state, so I'll give an output. So for example, here my initial state is suppose Q0. So I have already in the initial state, I have an output of 1. I go from Q0. Yeah, question?
No,
I
no,
go
no
from
question.
Q0 to Q1 and I give an output of 0. So thus, on reading A, and maybe suppose you read a B and you are in the self loop. So and then you read B, you are in Q1, you have again an output of 0. So for the string AB, the Moore machine gives an output of 1, 0, 0. So this is my output, right? And I can also consider a DFA to be a Moore machine such that, like on my final states, I give an output of 1, on the non-final states, I give an output of 0. And I can say that all those strings for which I get some 1 at the end should be the output should be such that at the end you get a 1. Those are the strings which are accepted, right? So it's like a 0, 1 kind of it. The DFA can be thought of as a Moore machine which gives output either 0 or 1, right? Okay, so let's try to define the Moore machine formally. So now you have so what was the DFA? So you had the 5 tuple Q sigma delta Q0F. This was my DFA. Now I have a Moore machine in which I have this lambda. Sorry, there is a delta, capital delta, I write, which is the output alphabet. And there is an additional, let's say, I also give something like this. And now, so let me put this in a different color. I have this, and I also have a lambda. So what is this? Okay, I'll tell you. So this is my output alphabet, and this gives mapping from states to output. Clear enough? So this is the mapping from states to output. Okay, so for example, now suppose if you have an input, so what is the type of lambda? So can you tell me what is the type of lambda? Q2? Sorry? Q2 delta. So this is the type of lambda. So it's clear, Ankit?
Yes, sir.
Okay, good. So you have this, and now you have an input. Let's say you have for an input, suppose you have A1, A2, A3, some AN, or in greater than equal to, let's say, or I don't know, maybe it can be 0 also, something like this. Okay, so what is the output? The output is, if the corresponding run, let's say Q0, Q0, Q1, etc., then the output that you are going to get is lambda Q0, lambda Q1, lambda Q1, right? So this is the output. So you see that the length of the output is 1 more than the length of the input. Clear? So the length of the output is 1 more than the length of the input. Okay. And here you essentially have where you have qi minus 1, ai go to qi, right? So the output is this, where qi minus qi minus 1, ai you go to qi for I in this set. Okay, good. Now let's consider an example. So suppose I talk about this example, which is like a Moore machine, right? Over the alphabet sigma equal to AB, okay? And there is a delta, which is of the form 0, 1, 2, and the behavior should be the following. So if you see a sequence AA, right? Sequence AA in the input, it should output 0. If you see sequence BB in the input, somewhere in the input, then output 1, and otherwise output 2. Okay, so you were reading this thing, and whenever, suppose, let's say you start with, let's consider some word A, B, okay, A, B, A, A, B, A, B, B, A. Okay, so we do something like this. So initially, you are at 2 because initially you have not seen any of these patterns, so you start with 2. You see the A, you still give 2. You have seen AB, you are still giving 2, right? So these are the transitions and these are the states, right? And then when you see an A, you are still at 2. But now when you see the AA, then you output 0. Then B, again 2. BA, 2. Then again B2. BB, you output 1. And then again, like this. Okay, so can you draw this Moore machine? Right, can you draw this Moore machine? So you'll initially start with a 2. And then what do? When you see an A, you'll go to some place which is also gives you a 2. Right? If you just see another B, you can, let's say, you still see a 2. So I've seen 1B. I have to remember that I have seen 1B here, right? And if I see a B now, another B, then I should output 1. Correct? So if I see another B here, then I should output 1. Right? But if I see a A here from here, then I should output a 0. Right? So I should output a 0. Right? And if I see A, I'll keep on outputting this thing. Right? I mean, I think you should try to do yourself so that, but just check. So what should be there on this edge? What is there on this edge? A B, right? And then where do I go if I read an A? Where do I go? So from here, Where do I go if I read an A? Q1, very good. If I read an A, right? Because you have seen one A. So this state remembers that you have seen one A, right? And then if you see, you can see another. Okay, where do I go if I see another B? Ankit? So from here, where do I go if I see a B?
From here, sir?
Yeah. So where do I go? Like from this state, where do I go if I read a B?
I'll be on this state only because I'll be seeing
Yeah,
double
sure.
B.
Very good. Very good. So okay. So and then this is right. This completes that. Right. Good. So now we will define something called a Mealy machine. Right. So why are we studying this? So these are automata with outputs, and there is a rich theory of these formal models which are called transducers. It's a rich area of study and an active area of research, which is called transducers. And these Mealy machines and Moore machines form the most basic form of transducers. Like it's so Mealy machines and Moore machines are actually basic transducers, right? Right? It forms some very basic transducers on these ones, right? So there can be transducers which can be much more richer. I mean, you can consider non-determinism in the transducer, right? Then, like, so we are talking about like the underlying automaton on the input. It's like a DFA, but you could also have considered an NFA. Then what happens? It's not going to define a function, but it's going to define a relation, right? It's like for one input word, you can have several output words. So it's a relation between input and output. It's no longer a function if you have non-determinism, right? And we have not really looked at non-determinism. So it gives you a relation between input and output. And we have not really looked at so far two-way automata, right? So there is something called a two-way automata where the head can move to the left as well as to the right. You can also think of two-way transducers. And then you can think of like the questions one would like to ask is like you give all these different kind of things, like just the way we saw, you have DFA, NFA, epsilon, NFA, then we ask these expressiveness questions, right? And NFA, non-deterministic automaton, can be equivalently translated to a DFA. If you have this kind of questions on transducers, is it going to be the same? Okay, corresponding to a non-deterministic transducer, does there always exist a deterministic one? Or you can ask, like, if I consider two-way automata, which for the case of just automata without outputs, like you can consider a DFA, but now the head can move on the input on both sides. And what one can show is that you can construct a one-way automaton of exponential size from a two-way automaton, right? It's again, this again accepts the class of regular languages. Also, we looked at universal automaton, right? Where you had all runs had to be accepted. They also accept the class of regular languages, right? And similarly for the two-way automaton. Now, what if you consider transducers where you have outputs? You consider two-way automata. You consider non-determinism in the transducer. Are they equivalent or are they going to give more expressiveness, right? So these are the interesting questions one would like to ask. So there is a rich theory here. And what we are possibly we may look at some of these things, or I'm not too sure, depends on how much time we have, or one can take this up as one of the seminar topics. I mean, I can give material. So this is the thing. So now Mealy machines. So what are this? So Moore machines had outputs on the states, right? Moore machine has output on the states. Mealy machines have outputs on transitions. Mealy machines have outputs and transitions, right? So how is your, so again, like I can talk about, for example, let's say Mealy machine, and right. And often in the case of Moore machines, you can have these inputs and you can have the corresponding outputs. And often it is the case that people may not talk about this final state, right? I mean, in the case of Moore machine, you can just, so this is my Moore machine, right? You have, right? And often it is the case that people will not talk about, for example, this final state. So the automaton is moving and then you are producing the output, right? It's moving over the inputs and you are producing the output. Now, in the case of Mealy machine, so you can have Q sigma delta Q0. And now this is the mapping from the transitions to the output. So mapping from the transitions to the outputs. So what is the type of lambda now? Right? So this is our output alphabet, and this is this thing. So what is the type of lambda now? Q cross sigma to delta. Correct? So I would say lambda QA is the output associated with transition Q1 input A, right? So this is the thing. Okay. And now similarly, if M is a Mealy machine, the output of M on a word W equal to A1 to AN is lambda of Q0 A1, lambda of Q1 A2, right? Lambda of Qn AN, where Q0, Q1, Qn is the sequence of states, right? Such that delta Qi minus 1 Ai equal to Qi, right? So this is the corresponding run. So very simple. I'm just talking about for I belonging to. I'm just writing it a bit formally. That's all. Correct? Now, if you see in the case of Mealy machine, the length of the output is n for an n length input, right? So as you see, for n length input, the length. Whereas in the case of Moore machine, so this is Mealy. Whereas for the case of Moore machine, how much was the length of the input? Length of the output for an n length input? It was n plus 1. Yeah, very good. So this was n plus 1. The output was n plus 1, whereas in the case of Mealy machine, it's the same right. So let's try to again have an example of a Mealy machine. Example of a Mealy machine. So you know what a two's complement is, right? So if you have, let's say 1, 1, 0, 1, what is its two's complement? So 1's complement is 0, 0, 1, 0, and 2's complement is 0, 0, 1, 1, right? So 1's complement, you just flip the bits and you add 1 and you get 2's complement, right? So this is the 2's complement, right? So all I want you to design a Mealy machine for which will compute the 2's complement. the question. Design a Mealy machine that gives the two's complement on an input. Okay, so tell me. I mean, yeah, it'll need a bit of a thought and tell me what is the answer. And you can try it, take a couple of minutes. And okay, so of course your sigma is, oops, sorry. So your sigma is going to be 0, 1. Your delta is also going to be 0, 1, right? And yeah. So look at the pattern, what is happening here, right? And then you can tell me what is our evaluation. Right? And when you are designing the Mealy machine, you have to think in which direction it reads. So the way I would do it is like you can read it from this direction, from the LSB. Okay. Read from the LSB. Okay, so yeah. So I would say just as a read from LSB, and you will find the pattern. Like, so what is happening? I can't hear you, sorry. So everything is complemented after the first one. But here you already have a first one here. It's not complemented. Huh? Oh, after the first one, is it? Okay. So let's look at something else. So let's say 1011. 1. Okay. So you have or let's see this. So you have 0, 1, 0, 1, 0, and you have 0, 1. Right. So you are going to add 1, right? So now if you add 1, you get a 1 here, 0, and 1, 0. Right. So indeed, after the first one, so if you, let's say you have 1, 0, 0, 1, 0, 0. So then you get 0, 1, 1, 0, 1, 1, and then you get, what do you get here? 1, 0, 0, right? And here, this is like this, right? So where is your first one? Everything gets complemented. And until then, everything remains. Okay, so how can you draw this now? Can you draw it? So Bikhan was saying that after the first one, everything gets complemented in the two's complement, right? So it's kind of easy. Like you can, whenever you are getting a 0, you keep on outputting 0. You get a 1, you output 1, but now you go to a different state. And here, if you get a 0, you output 1. If you, oops, here, if you get a 1, put 0, right? So you have to remember the first one. Clear? So this is 2's complement. Clear, Ankit?
Yes, it's clear.
Okay, okay, good. Right, so you just have to look at the first one, and then this first one takes you to another state where you start getting different kind of things. Right. Now, one thing, let's finish. Hopefully, we'll be able to finish this. Equivalence between Mealy and Moore machine. So what are we saying? Given any Moore machine, so first let's say we do this direction. It's an easier direction. Moore machine to Mealy machine. Right? So you have outputs on the states here in the Moore machine, correct? And you are going to take consider a Mealy machine in which the outputs are going to be on the transitions, right? On the transitions. Now here there is an output, let's say, but there is also another consideration, because here there is some the length is n+1. The output length is n+1, and there the output length is n. Length is n. So what we will do is, like, let's say for the initial state, so you cannot have a direct translation, but let's say for the initial state of the Moore machine, the output is b, right? And then what we'll say is that this is, if the output is, let's say, here lambda of w, here also we want it to be b of some lambda prime. I'm saying lambda prime because it's on the transition, and so lambda and lambda prime. So here you have some machine m, here you have a machine m prime, and the output, if the initial state, right, if the initial state, if lambda of q0 equal to b, then I would like to output on w b lambda prime w. Now, right, so how would you do that? How would you translate a Moore machine to a Mealy machine with this assumption? So you are going, let's say, from Q0 to Q1, from Q1 to Q2, and here, let's say the output is 0, 1, 0. And all you want is to output, like the initial, you can forget, it's the B. You want to output on the Mealy machine a 1 and a 0. So what is the general translation? What is the general translation? Sorry? Take the output to the, I don't hear you. Take the output to the incoming transition, to the next incoming transition, right? So how do you write it formally? You are right. Take the output to the incoming transition. So suppose I have, let's say I have my m prime. If my m is, say, q sigma delta q0, m prime is, let's say, I'm missing something here, lambda, and this is q prime sigma delta lambda prime q0 prime. So first of all, what is the q prime here? What is the state space q prime here? What is the state space q prime here? Ankit? What is the state space q prime?
Q prime should be
The same as q.
yeah, same as Q.
We are just moving. So the idea is that we are just moving the output from here to this thing. Okay, on the input. Okay, it's just on the transition, right? And so q prime equal to q. what about what about the Q0 prime? It's the same as Q0, right? The Q0 prime here, the same as the same initial state, right? So as I was saying that you are moving from Q0, Q1, Q2, and I'm also doing from Q0, Q1, Q2. It's just that whenever I was seeing the output here, right? Q0, 0, Q1, 1, Q2, 0. I'm now moving these things like this, you can ignore, right? Because of the mismatch in the output length. And the output on this state, you are going to put it on the transitions. Correct? So what is now, how am I going to define lambda prime? Lambda prime of some q prime comma, let's say a, equal to
Sir, I'm not able to. Where is your screen, sir? Where writing? I'm not able to see that.
okay, it's at the bottom. Okay, so let me go to another page, or maybe I'll just minimize this a bit.
That's fine.
Okay, so I'm going to define the lambda prime. I'm going to define the lambda prime. So what is the lambda prime? It's the output. So what is the type of lambda prime? It's q cross sigma to q. What is the type of lambda? It's a Mealy machine, right? What is the type of lambda? It is q to
Q
delta. Sorry, here it is delta. Correct? So the output is on the transition. So this says that the output on transition, it's a Mealy machine, and it's output on it. Right? Now, how are you going to define the lambda? Yeah, tell me. Sorry, lambda prime of some q prime comma a equal to lambda of delta of q prime comma a. Right, good. So is it clear?
Yes, sir.
Ankit?
Yeah.
Why do we have a delta there? Why do we have a delta here?
Because of this, because we are putting on transition function, output on transition function.
No, so which one is the output on transition function?
So this delta, I mean, this delta I'm taking straight to the, I mean, output actually. Okay.
No, so what is the delta? What is delta?
Delta is my state to output transition.
Yes.
So I'm taking because on Moore machine my output is on this on the state. Okay.
Mm-hmm.
So that I'm moving to the transition actually.
Yeah. So you are moving this output on the state in the transition. But why does this delta come? So why it is not lambda? So the question is that why it is not lambda of q prime, and why it is lambda of delta of q prime comma a?
Oh.
Why it is not lambda of q prime? Right? So what are we saying? We are saying, so if you follow here,
Okay.
so if you follow here, then what are we saying? That, so suppose there is this q1, correct? So
Okay.
q1, there is this output on the q1, and we are putting the output on the incoming transition to q1, right? So the output of q1 is put on the incoming transition.
Okay.
Okay, right? So now if you are putting this lambda prime of q prime, so it's this q prime comma a, right? Q prime comma a is this transition. But what is this q prime? This q prime is actually this q0 here, right? Because it's the q prime a. So I'm talking about this transition. So this transition is nothing but q0a, correct? This
Yes.
transition is q0a. So I'm defining the transition on this one. But the output here is coming from the output of this state in the Moore machine, right? Now, what is this state? This state is delta of q prime comma a. Delta of q prime comma a is the q1.
Yeah.
And the lambda of this in the Moore machine, the lambda of this state is the same. This one, the lambda of this output is the same as this thing, and this is nothing but this transition is nothing but the q0 comma a. So that's why you have the delta here.
Okay, fine.
Is it okay?
Yeah, it's fine, sir.
Okay. So, right. So you can now, I mean, okay. So we just define. So, but you also have to prove that indeed, prove that indeed the two machines, indeed M prime. What is M prime? The Mealy machine we constructed, and M are equivalent. Right? So to prove it. And how would you prove this? We are not going to do this proof because we have done something similar several times.
Yes.
Sorry?
Yes, so we will take
how are you going to do this proof? Like, what is the basic idea of the proof? Like, what would you do in order to prove?
We will take on words, okay?
Yeah, you will consider input words and
I will look at the not the transition function. I mean the delta. Can you just go back a little bit?
yes.
Just one page back. Yes. So here, no, just from next page, sir. Yeah, here, sir. So here I have defined this delta prime q prime comma a. In place of a, I will take my word, okay, and then I will try to prove that it's delta. Not I'll make a star or something that function, okay, and prove that it is equal to this lambda inside delta q prime wh.
Okay, so I think I kind of followed what you were saying. So primarily, as Bikhan also you were saying, so we'll do an induction on the
W.
length of
W.
the input word, right? And this is something you should try out yourself now,
Okay.
right? So these are, unless you do these things, you won't learn. Like, so this should be kind of another homework. Like, you should try these things yourself. Unless you are trying these things yourself, you won't learn like how to do this. So I would leave it here. So think about this. So think about this. We will discuss it. When I say this homework, it's mostly like you have to think, but it's not like you have to submit something. It's more like here at least, or I would say, think on this. How to translate for the other direction? How to translate a Mealy machine to a Moore machine? So the other direction was very easy. The Moore to Mealy. You just took it. Here you have to do the Sorry. Oh, okay. That's okay. Yeah, but
can we not move what is the output on the transition function to the state that it is going?
Yeah, so something of that kind. So just keep thinking about it. So I think we'll have to sort of like, we are running out of time. So this is something you should think, okay? And so we are going to meet on next Tuesday. And before we end, Any questions today, right? So what did we look at? So we looked at extended star height, and we looked at some of the open problems there. We looked at finite power property, and we talked about some homeworks, some assignments which you should do yourself, spend some time just to be more familiar with these definitions, to make yourself more comfortable. That's all. That is the purpose. These are not very difficult problems I'm giving. Just if to make sure that you understand the definitions and follow them. And so next, you should also think about this. And next lecture, we will look at this equivalence quickly, and we will look at some other closure properties. Like one thing that we are going to study carefully in the next lecture is the notion of homomorphism. This is an interesting. This is a very important thing in this area, and we are going to start with this in the next lecture, homomorphism. Okay, and it will be also required to some extent for in algebraic automata theory, and we are going to look at them. Okay, so I'm going to stop now.